there's a bit of a challenge there. Now, there's the hexapedal locomotion is pretty promising. It's statically stable, it's easy to control, it's rapid and all-terrain, you don't need many actuators. And what we found recently is that it's also unexpectedly very geometric. That is, dynamics don't seem to play a role even when there's a lot of slipping. In fact, that's what I talked about in last year's dynamic walking and in another presentation at the APS. So what I talked about then was that we had a remarkable success with a very non-conventional friction model in predicting how these multi-legged systems are going to move, and that raises a difficult puzzle because that friction model is predicting individual leg forces. Those don't necessarily give rise, even if we see the right body motion, it doesn't mean that those were the actual ground contact forces. So to disambiguate that question and figure out whether this weird friction ansatz was correct or not, we need to measure those individual leg forces and not just the motion of the center of mass. And more generally, it would be really interesting to know how that static indeterminacy is actually being resolved by robots moving. And so I went to the person who has funded much of my research in the Army Research Office and asked him for a whole lot of money to put very expensive 6-stop force transducers on a robot. This is actually the most expensive robot I ever built. And that's just because of those 3 devices there that are attached to the legs. So this is the hexapedal robot that you built for me. It is very similar to the hexapedal version in the previous talk from my lab that Dan Zhao gave a little while ago. Elastic legs. These legs go across the body. So there's actually 3 legs, but each of them plays roles on both sides. And the way we then solve for the ground contact forces is because only one of the feet is on the ground at any point in time, at least ideally on each of these legs, we can transport the force and torque at the contact where the transducer is all the way down to the contact point and figure out what the contact force was. And so after some painstaking work, you managed to do that, and you know he's a very tenacious guy. I wish he was here to impress you all because he's looking for a place to do a PhD, and he should advertise himself. But here's some preliminary data from that system, where we can actually see the motion of the feet in 3D. So these are feet lifting on and off the ground. There's a region where both feet on a leg are in ground contact, and we can't resolve the individual foot forces, but in the regions that we can resolve the individual foot forces, they actually look pretty nicely periodic. And so at least what we're seeing is that stride to stride, there isn't some weird exchange where the load is shifting in the body of the robot. What it's doing every cycle is basically the same. Of course, the next thing we need to do is take these data and compare them with the prediction of our unconventional friction model and see whether these predictions pan out. And that I will probably tell you about in another year or 2.
Right.
So thank you.
Okay, I see there's a question.
Yeah.
So is there anything in these results that could potentially change the way you do control for a hexapedal robot? It seems like that the sort of body motion measurements that you do have are largely the kind of things that you'd be concerned with in control.
Well, I would say that my talk last year is really where the control surprises came, because what it showed us is that you can use a connection type model, a model that has no dynamics whatsoever, to deal with these multi-legged systems even when they're slipping. So including slipping, which is actually a great thing when you have multiple legs, because you can get better maneuverability by having the legs slide on the ground. You can still model things very well without having second order dynamics at all, without having forces. It's just a kinematic model, which is pretty cool and has a lot of potential in planning. Yeah.
Questions?
If the feet are slipping and you're measuring the force between the foot and the body, All right, do you have to do some sort of inverse dynamics or forward dynamics to account for, to sort of resolve if the whole system is just sort of transmitting or not?
Well,
Using the
so,
mocap, yeah.
so there could be inertial forces that need to be taken into account there if the masses were big. They're actually pretty small compared to the mass of the robot, so these legs are very light. So the inertial reduction, because the leg is accelerating relative to the body because it just got out of the friction cone and slid, it's not going to make huge changes. But you're right, there is a correction term that would need to happen there if something is accelerating.
Even if it's the body accelerating, not just the leg accelerating?
Well, the force is between the leg and the body, right? This is the force we're measuring. But what you are correctly pointing out is that if the leg is accelerating with respect to the ground, then the force between the body and the leg and the force between the leg and the ground have a bit of a more complicated relationship.
Yeah, so just a question. My understanding is that you wanted to make a measurement and then later verify the model.
Well, we have a model that seems to work really well, except it has the physics wrong. So that's kind of disturbing. And so we wanted to make measurements to figure out whether the model was right and we were wrong about the physics, or the model is wrong in a way that happened to get the right result.
I see. This is the ground truth that you want to generate.
This is sort of in the middle between what the model is predicting and what the world is doing, because the world is aggregating forces through the feet, and we see the outcome, and the outcome was right. So now, somehow, if what each foot did was what the model said it would, that would be great, but that has the wrong friction model. And so that's what we're trying to figure out.
Question?
Did you check the last line in each of those plots, the vertical forces?
The last line is actually the height of the foot.
That's the height of which one is the vertical forces?
So this is Z force, Y force, X force.
Meaning which one is which?
So Z is vertical, X is along the body, Y is lateral.
Okay. One more question.
What's the wrong friction model?
So the wrong friction model is that we are using a force that looks like this. Tangent force equals normal force times mu times minus velocity instead of unit vector in the direction of velocity. So it's linear in contact velocity instead of just being in the direction of the velocity.
Shai, there's one more question. Go ahead.
Direct measurements from the sensors that you put on the robot.
Yeah.
So you could directly just say if the model is predicting the right forces or not.
We could, but I don't have these data for this robot yet. So you're right that this is not a huge step.
All right, great. So let's send the speaker again.